So the first line of the title of this slide is the same as the previous one, reactivities/stabilities of acids and derivatives. In the last one, we tried to explain the difference in reactivities, starting at acid chlorides, going all the way down to amides, in terms of the relative stability of the molecules. How much could that electron density be shared out? The more it could be shared out, the less reactive the molecule, because the more stable the molecule. Now we're going to look at it from the perspective of reactivity by looking at the role of these different species and their differences and similarities in the mechanism of the big reaction that they undergo, so-called nucleophilic acyl substitution. Now I want you to think about these three words. Nucleophilic, of course, attack by a nucleophile. Acyl is the acyl group, the RC double bond O group, that's the foundation of all of our acids and derivatives. And substitution, meaning that the nucleophile stays, something else leaves. So here is a general structure of our acid and derivative. So X can be Cl for an acid chloride, OH for an acid, NH2 for an amide, and so on. But I've drawn it like this to indicate the similarity to what we saw in the last module. If X was H, this is an aldehyde. If X is an alkyl group, it's a ketone. Regardless, whichever type of molecule it is, you have a carbon double bonded to an oxygen. So this carbon is slightly positive. Slightly positive things are extremely appealing to nucleophiles. So a nucleophile comes in with its lone pair of electrons, pops into the carbon. Carbon says to the oxygen, well, you know those pi electrons we were sharing, feel free to take them as a lone pair. In fact, I insist. And so we get this tetrahedral intermediate that should be very familiar to you from the last module. Okay, if this was an aldehyde or a ketone, then we would see this same tetrahedral intermediate, but now we would protonate the oxygen and we would make our final product. If our attacking group, the nucleophile, had been water, this would be one of those gem diols. If on the other hand this had been Cn-, this would have been a cyanohydrin. But when you've got the X is an aldehyde or a ketone, X is H or X is alkyl group, you end up making a saturated carbon center, a carbon with four things in the product. However, we're not adding, we're substituting. So what happens when X is Cl down to NH2, in other words, where X is one of those very electronegative atoms, is that the lone pair of electrons that had moved on to the oxygen pops back in to make a pi bond with the carbon, and the carbon tells the X to leave. And so we have this substitution product in which now the nucleophile has replaced the X. Okay, and so we have a leaving group, and that's the crux of this discussion. The X that was, of course, our derivative, or the acid, the Cl, or the OH, or the NH2, has now left. Let's make it very clear what those leaving groups are. When we have an alkyl halide, any reaction, the Cl- leaves, and we got the new species on here, the nucleophile on this carbon. Okay, so the leaving group is Cl- for an acid chloride. When we have an acid anhydride, the leaving group is an acid conjugate base. Okay, we've lost this bit down here, the R prime C double bond OO, that's gone. The acyl group here bonds to something new. So that's the leaving group, is the conjugate base of this second acid here. When we have an acid, of course, the leaving group is OH-. When we have an ester, the leaving group is RO-. That is the conjugate base of an alcohol, a so-called alkoxide. And of course, if we have an amide, the leaving group is NH2-. Okay, so the reactivity here is all going to be about that leaving group. Okay, how happy is that leaving group to have left? Okay, so what we need to argue is, what is the stability, the relative stability of this leaving group? Okay, the more stable the leaving group, the happier the leaving group is to have left, the more reactive the species. And in order to compare these leaving groups, we think about their basicity, because that's essentially what's going on, isn't it? What we're saying here is that this X, right, is sharing electrons. It's giving electrons. It's donating electrons to the carbon. We can think about it like that. So the more that it wants to donate electrons, the stronger the base it is, the less likely it is to be happy all by itself. Now, how do we compare the basicity of these things? Right? Well, we can look at the conjugate acid. Okay, remember, the weaker the base, the better the leaving group. So let's think about not the base, but its conjugate acid. So what's the conjugate acid of Cl minus? Well, it's HCl. HCl is an amazingly strong acid. Okay, going all the way down, what's the conjugate acid of NH2 minus? Well, it's NH3. You don't think of NH3 as being an acid, do you? Think of it as being a base. Okay, and we can get that idea going from a strong acid to a base by looking at these pKa values. Right, we want very weak base. Okay, well, as acid strength goes up, the base strength goes down. Okay, so we want the weakest base, which means we want the strongest acid. Okay, now as the acid strength goes up, the Ka goes up. As the Ka goes up, the pKa goes down. So in other words, the lower the pKa, the stronger the acid, the weaker its base. So now let's look at these pKa's here. -7, that's a pretty small number. In fact, it's so small, it's negative, okay? Because, of course, we know HCl is a very, very strong acid. HCl is a very, very strong acid. Cl minus is a very, very, very weak base. Cl minus is a very, very, very weak base. Thus, it's a very good leaving group. Down here, NH2 minus as the leaving group, well, NH3 is not an acid at all, it's a base. So it has a really big Ka. If it's got a really big pKa, it's got a really small Ka, which means it's a very, very weak acid. If it's a very, very, very weak acid, that means this is a very, very, very strong base. If it's a very, very, very strong base, it's a terrible leaving group. So you can see that as we look at our reactivities, okay, the most reactive is the acid chloride, because Cl minus is a wonderful leaving group. The least reactive is NH2 minus, because NH2 minus is a terrible leaving group. Now we can look at that disparity, that issue between the acid anhydrides and the acids, if we want, and the alcohols. The leaving group for an acid anhydride is the conjugate base of a carboxylic acid. It's a pretty good acid. As this is a pretty good acid, this is a pretty weak base. As it's a pretty weak base, it's going to be a good leaving group. OH minus is a strong base, not as good a leaving group. RO minus is definitely a strong base, not a good leaving group. But now look at, do you remember I said earlier that some acids and some esters about equal in reactivity? That's because their pKa's are certainly in the same ballpark. Okay, so we've got very, very negative pKa, very strong acid, very, very weak base, very good leaving group, all the way down to pathetically weak acid, very strong base, terrible leaving group. And it very definitely goes in the order acid chloride, acid anhydride, acid, an ester, and then all the way down amides.